Okay, I'm on number 3 in your packet. This one's considerably more difficult than 1 and 2, not as straightforward. So let's kind of think through this one together. I'm going to at least get you started on it. If you haven't read the question, pause the video, read the question, and then start it again, and we will talk about what to do. Okay, part A. There is a lot going on in part A, and I'm not surprised if you're looking at that saying, I have no idea what I'm supposed to do right now. Part B, similar to what we saw in number 1, part B is the one that is very similar to what we have done, and we'll get to that. So if you were thinking, solve the differential equation, separate your variables, fine, but that's going to be part B. So let's try to tackle part A. We need to find the particular solution so that the line y equals -2 is tangent to the graph of f. I want to focus in on this phrase right here. So we know something about a tangent line. Think about a tangent line. And the line y equals -2 is a horizontal line. So our tangent is a horizontal tangent. I like to think visually, so I'm going to draw a random graph. This has nothing to do with what this function actually looks like. But here's what I'm picturing. I'm picturing I have some curve. I don't know what it's doing. And at y equals -2, so I don't know where it is on my x's, but I know that at y equals -2, so let's just pretend that this is y equals -2 right here. Hold on, let's try that again. That was supposed to intersect my graph. At y equals -2, I have a horizontal tangent to the graph of f. So like I said, don't know what x is, but I know that my horizontal tangent is going to occur when y is -2. I need to find the x-coordinate of this point of tangency. So what exactly is my x-coordinate to that point is what I'm trying to figure out. And then decide if it's a local min or max. So let's first figure out how can we figure out what that x value is. And I'm going to go with, think about what you know about a horizontal tangent. A horizontal tangent is indicating a slope of what? 0. So I know that my slope at that point, in calculus, we use what to refer to slope? Derivative, or dy dx. So my dy dx is 0 when y is -2 and x is question mark, don't know. So how can I use the given information to help me? Well, they gave me an equation that relates slope, dy dx, with x and y, and it appears that I have two of those things. I've got my dy dx right here, and I've got my y right here. All I've got to do is solve for x. That's going to be my unknown in that equation. So I'm going to grab that equation. Dy dx equals 3 minus x over y. And now I'm going to rewrite it, but I'm going to use the information that I know. So now I know that my dy dx is 0. So 0 is equal to 3 minus x is my unknown, but I do know that my y value is -2, so that's going in the denominator. So from here, it's a solve for x. So I've got 3 minus x over -2. I'm going to multiply by a -2, or you could have thought make it a proportion, put it over 1. -2 times 0 is still 0, so nothing's changing on the left, but I now have a simpler right side, and I'm going to finish that off by adding x or subtracting 3, and you're going to get x equals a +3. I believe that was the first part of the question, find the x value, and by some miracle, my graph is actually not too bad. It does look like I'm over 3, but again, that was just a random picture, literally, that I drew. So let's see how we're doing. Find the x-coordinate of the point of tangency. So that one is x equals 3. Part 1 done. Determine whether f has a local maximum, minimum, or neither at this point. So now I need to consider the graph of f, which is my solution. So right here, I graphed my solution, or I did a sort of a rough sketch of having no idea what it looks like possible graph. But I need to figure out, is it actually a minimum? It looks like I drew it as a minimum, and that was just, again, a random graph. Is it a minimum, maximum, or neither? So to do this, we need to be thinking how do I know if I have a minimum or maximum on a graph? I'm just going to ignore the rest of the question for right now and say, how do I know if I have a minimum or maximum? My answer would be do this, if that rings a bell. So we're considering the point 3, negative 2. So normally I just put down my x value. And I first need to see, is my f prime 0 at that point or undefined? Is it a critical point? Well, yes, they told me that my derivative, same thing as f prime, dy dx, is 0. So I would be considering signs on either side, positive, negative. Now, here's the problem. Because we're considering x and y, my derivative is defined in terms of x and y. I can't just pick a negative or an x value less than 3 and an x value greater than 3. Because let's just suppose I pick 0 for my x value. 3 minus 0 is 3, that's great. But depending on what my y is, my slope could be positive or negative. If it's 3 over a positive y, then I would have a positive value. And I don't know what's happening with my graph to know if at 3, my y value is going to be positive or negative. So this is a case where my first derivative test, which is what I was doing right here, my first derivative test to give me signs telling me my function is increasing, decreasing, etc., fails. No good. So I just don't have enough information to use it. I'm going to have to use what we call our second derivative test. And we looked at it very briefly. I don't know if we've ever used it, like had to use it. I showed you how it would work, but we really haven't used it much because we haven't had a reason to need to use it. This would be a reason, and basically it's because my derivative is defined in x and in terms of x and y. Second derivative test should make a lot of sense to you. So before I even do it, I'm just going to go over the concept. The concept is, if I'm going to have a minimum on my graph, I know that if I'm going to have a minimum, my graph is going to have to be concave up, which means my second derivative, f prime, is going to have to be less than 0. And if it's going to be a maximum, it's going to have to be concave down at that point, which means my second derivative is going to have to be greater than 0. And if it's going to be, I don't know if we'll be able to get, from our second derivative test, I don't think we'll be able to get if it's neither. Unless it's 0. We know if my second derivative is 0, it's not going to be concave up or down. But let's go ahead and see, at that point, as long as it's not 0, we should be getting a minimum or maximum. So I don't believe I have my second derivative. I'm going to need to do that. But because I have my derivative given to me, I can calculate my second derivative, and then I can evaluate it at the point 3, negative 2 to see what's happening. Y dx equals 3 minus x over y. I'm going to take the second derivative. So second derivative of both sides, or derivative of both sides to give me the second derivative, is equal to, I'm going to have to do quotient rule. Good review of your derivative rules. So I've got denominator times derivative of the numerator is negative 1. Oops, not plus. Subtracting with quotient rule, minus numerator. 3 minus x times derivative of the denominator is 1, but I've got to multiply it by dy dx. I'm doing implicit differentiation, and that is all over y squared. From here, a couple options. We know that we can now take our derivative and plug it into our second derivative, because with implicit differentiation, you want your answer to be in terms of x and y exclusively and not have a dy dx in it. I ultimately am going to be solving for the second derivative at a point. So in this case, just to not waste a lot of time tidying up something that's not going to give us an answer and potentially cause us to make an algebra error, I'm going to see if I can go ahead and substitute in. So again, I'm evaluating it at the point negative 2. Whoops, no, negative 2 is my y value. Take that back. Evaluating it at the point 3, negative 2, because they told me y is negative 2, x is 3. That was the first thing that I solved for. I want to know what is my second derivative at that point. For now, let's just find it, and then I will again explain what it's telling me. So I'm going to go ahead and substitute in everything I know. Negative 2 is my y, and that's times negative 1. Minus 3 minus x is 3. times dy dx. Recall that your dy dx, that's my slope. And my slope at the point, because I had a horizontal tangent, I had a horizontal line, y equals -2. I know that my slope is 0, but if you're questioning that, let's go ahead and just do a quick check. My quick check would be, let's actually solve this up here. dy dx at the point 3, -2. So that would be 3 minus x is 3 right here, over -2, because my y value is -2. And that's going to give me 3 minus 3, 0 over -2, and that's how I'm confirming that yes is 0. So my slope is 0, which means I'm going to put my 0 right here. That's where I got that from. All over y squared, and my y was -2. I'm squaring that. Simplifying that, let's see, we're going to end up with -2 times -1 is +2. 3 minus 3, this is 0. So I've got 0 times 0, so 2 minus 0 all over -2 squared is a +4, which is giving me 1/2 for my second derivative at the point 3, -2. Why do I care? Second derivative test tells me if my second derivative is equal to 1/2, which is greater than 0. This is the only part that I really need, this greater than 0 part. And I know it's greater than 0 because I just found it to be 1/2. Then there has to be a local minimum, as long as that's a critical point. So I already know that 3, -2 is a critical point. There has to be a local minimum because my graph is concave up whenever my second derivative is greater than 0. Okay, this is kind of the, you don't really need to include that. Second derivative test allows me to just jump to the local minimum, but I'm explaining why. So total answer to part A would be x is 3, and then at that point you have a local minimum because your second derivative is greater than 0. This would be key because it says justify your answer. You would need something about that the second derivative is greater than 0, therefore a local minimum. Okay? Good work. That was a lot of work for part A. Part B, I said, was more straightforward. So I want you to go ahead and do part B. The hint I'm going to give you with part B is you are somewhere in there going y squared. I'm not going to go through the whole thing. But you're somewhere in there going to get, once you take the integral of both sides, y squared equals some stuff over here with your plus c. And you're going to solve for that. But when you solve for y, you're eventually going to be taking the square root of both sides. Remember, when you take the square root, you have a plus or minus option. So if you're looking at part B, they give you the information that you're only considering the interval from -2 to 8. So that might confuse you. You don't really need to even worry about that. What you need to worry about with determining whether you're going to have a positive or negative answer is you need to look at your initial condition. And your initial condition, so I would ignore this. Your initial condition is g of 6 equals -4, which means that you're looking at the point 6, -4. If you take a positive square root, you're never going to get a negative answer for y, because the square root of a number is always positive. So your ultimate answer is going to be a negative square root of something, and when you're considering this, you're going to ignore the positive, keep the negative, and we're keeping the negative because our initial condition tells us that we have to get a y value that's negative. Okay? I'm going to let you solve the rest of that because I think that you'll be fine solving it. I'm going to suggest maybe you actually solve for c before you take the square root of both sides. So solve for c when your equation is in the form y squared equals something plus c. Put in your initial condition, get your c, and then go ahead and go back. But that's up to you. It could work either way. Okay, so go ahead and try that one, and we can check that one later.